Hi everyone, thanks for coming to the presentation. Apologize for the delay, beyond our control sometimes. I'd like to present some of the work I've done on a fast approximate state estimation based approach to cybersecurity threat detection in power systems. The work I've done is in collaboration with Alfonso Valdez and Richard McGuan, who are both research scientists, research engineers at the Information Trust Institute at ITI. And Reynaldo Nuqui is the corporate partner in this project for us from ABB Corporate Research. And so I'd like to, before I start the presentation, I'd just like to give you a brief outline of the topics that we'll be discussing and hopefully lay the groundwork on what the problem is, motivate the problem, what are the current solutions of doing it, what we're essentially proposing as a means to address this issue. Some of the outlines on how we model this whole process, because we don't have a power system handy to work with, and the detection mechanism, some simulations, and some heuristic results on the detection mechanism. So why is it important these days? Well, essentially, as we've come to rely more and more on the cyber physical layer in power systems, so microelectronic based devices that do a lot of our control and operation and monitoring in large power systems, we are starting to open up an attack surface, which is a major vulnerability in the power system operation itself. So any individual or entities with malicious, we consider them as malicious, but they could be any sort of intention, can get access to that cyber physical channel and then tamper with any commands that are sent or received with, to achieve a variety of goals. They could be financial, they could be system deviations. And so one approach, the sort of standard approach in trying to mitigate these is in the realm of information technology, where we employ a lot of intrusion detection and prevention techniques on the signals themselves to check the authenticity of the signals. So we try to parse the syntax, make sure that the syntax has not been corrupted, which would be one signature if the signal were to have been corrupted. So what we are going to talk about here
is that the animation you're talking about?
Okay, well, it did work. Yeah. Okay. So what the approach that we are taking here is somewhat complementary to these IT-based solutions. And the sort of framework behind this approach is that if we are a system operator, or if we are someone responsible for the power system, we are privy to certain privileged information about the system that an attacker may not necessarily have. They may have some information, but it's not likely that they have the breadth of information that a system operator has access to. And so based on that, we leverage this knowledge to come up with an alternate means of threat detection. And the approach is based on essentially a state estimation method. And we call it a fast approximate state estimation because within this particular process, we make certain approximations to allow us to make these computations happen in much smaller time periods than is normally used for state estimation in power systems. As we all know, state estimation is already used in power systems, but the average time between computations is about 2 to 5 minutes. And we hope to basically reduce that margin to be able to keep track of a system's evolution in time at a much faster, at a much higher frequency. And to motivate the whole problem here, we focus on one particular case study. And the case study is essentially a large AC power system with a transmission link, a HVDC transmission link. And we'll focus on the threats that are directed at this transmission link. This is the case study for this particular instance, but this can be generalized in a much more broad setting. As we hopefully end with the conclusions, we'll see how we can generalize it. And so the case under study, I'll use the case to sort of motivate the idea here. The case that we are using is a synthetic model of of something similar in scale and size to the Western interconnect in the United States. So it has a major portion of the western part of the United States as in it. And this particular synthetic bus case was created by Professor Overby, now at Texas A&M. We use this particular system with the introduction of an HVDC link into it. So that dashed line there is signifying what in the real world Western interconnect system is the Pacific intertie. So it's a DC transmission line that goes between the borders of Oregon and Washington all the way down to the LA area. And it's used actually for a lot of congestion handling when the LA area requires a lot of power. The case that we use is about 2,500 buses and has about 5,700 lines in the system. So how does the basic layout of this whole setup work? Well, on any given time instant, the line flow that is required on the HVDC line is computed based on an optimal power flow solution for the whole system by the transmission system operator. And then they send this signal. So there is some megawatt flow required on this HVDC line. And this signal is then sent to the HVDC stations at either end of this line that will then implement this power order signal. All the controls at the HVDC stations are, as of today, they are local. In fact, until very recently, the dispatch signal used to be sent over telephone. In fact, wherein one person would pick up the phone and say, "Hey, this is Bob. Can you crank up the power flow on the line to 1,500 megawatts or something?" And the only security protection there is that, oh, I know the guy's voice, and that's about it. So all the controls at the HVDC station are local. They're operated by the local operator there. And so what is the threat? Essentially,
What are those ACCBs?
oh, I'm sorry. The ACCBs are AC circuit breakers, DC circuit breakers. Any capacitors and commutation transformer tap values, things like that. All those control variables are controlled locally. So the threat modeling, essentially what ends up happening is that there is no direct control on the breaker status and things like that from the transmission operator's control system. The only thing that we can then sort of target is what is that communication that happens between the operator's control center and the converter station. And that happens to be this power dispatch signal. So we are interested in investigating what happens when an adversary gets access to this communication channel and then alters that power order dispatch. So it's a false data injection type of attack, and we'll see what we can come up with on this here. So here's a graphical depiction of the threat. So imagine you have some large AC system, two buses of which are connected by some HVDC transmission link. So you have a converter control station and an inverter control station. So the assumption here is that the power is injected into the HVDC line from region 1 in the AC network. This power flows across the DC line, comes up to the inverter control station, and then it's inverted and injected back into the AC system at region 2. So the system operator would send some control power order dispatch signal to the CCS, and this may be their intended idea. So essentially, the line has some initial flow on it, and they wish the flow on the line to go up to some new value P1 DC in a certain time. When that signal is sent, an attacker could intercept this communication channel and then modify that value so that the person at this side here, the control operator, sees a signal that asks him to change the ultimate power order to some P2, which is different than P1. So this is essentially the threat that we're investigating.
Where is on this chart your transmission system operator?
So the transmission system operator, in some sense, would be this system operator control center.
Yeah, but why do you give it a different name? In the chart, the slide before, it was just transmission system operator, and now it becomes a system operator. Are you trying to confuse me or you?
I can change that. It's I mean, it's
Don't use both.
okay. And so the premises here is that the attacker, whoever this person may be, can only get to the telecommunication link that's between the system operator control center and then the converter control station. And he or she does not have the breadth to gain access to measurements that come from the rest of the AC system because they're far too numerous. And so it's unlikely that they will be compromised. So we assume that they are not malicious and they just have natural noise as a result of thermal processes. And the network topology, while this power order is being implemented, is assumed to not change. And so we sample the system at every instant in time when the power order is being executed. So as the line flow changes along the DC line. And we assume that at any of those time instances, there is no dynamic regime behavior in the power system. And so the detection mechanism is inherently pretty simple. What we're saying is that if the power order if I know the power order that I've sent, and I have a physical system that implements said power order, it's going to generate measurements for all the lines in the system. Their line flows are going to start changing in the system. So I can receive those measurements, and then I can use it to compute an estimate of my system state. Based on that estimate, I can then compute an estimate on the power injection at either of the buses that are connected to the HVDC line. And what I should naturally see is that whatever I estimate should be very close to what I had sent out. So it's an indirect sort of way to observe whether what I requested has been implemented or not. And so there are two possibilities. Yes, if these match very closely, then the system is working as expected. The implementation went ahead as expected. Or if it doesn't, then it's either been incorrectly received or incorrectly implemented, one of the two. So for our simulation strategy, what we essentially do is the case study that I showed you, the WEC case, we implement that in PowerWorld. So PowerWorld simulation software is our proxy for the real world system. So we simulate the power order as it's being executed in the software and generate line measurements for all the lines. And then we export them to something that stands in for a computational platform that would be at a system operator's control center. In our case, we use MATLAB, and the state estimation algorithm then receives these measurements and then computes rapidly our state estimation. And as I said, the estimated state then we use to compute an estimate of the injection at either ends of the DC line. So just standard equations for state estimation essentially is there is some state of the system that I do not
use the P2 injections in your state estimator.
No, I do not. So in this instance, the state estimation we use only is utilizing the line flow measurements.
Normally, you would probably use that, right?
You would, yes. But again, so the reason why we're not using those in this case is, again, if you were to use that, then it's sort of trivial in saying that I just want to compare what I sent with the injection I see. But again, it's just one single point that I can observe.
So, but how do you know to leave those out and do this? I guess that's
So yes, that's a great question. And essentially, that stems from the approximation that we make just a little further down, maybe a slide or two. But essentially, we make an approximation that allows us to, or we use an approximation to prioritize a subset of measurements. And then it so happens that that metric is usually used for line flow measurements. So I won't really go on about this, except just note the fact here that state estimation is Nonlinear state estimation is a iterative process. So there is some idea of the number of iterations that you need to do until you get some kind of solution close to a specified tolerance. So because it's an iterative process, it can sometimes take a while to converge. And when we are working in limited time budgets, we may not have that liberty. So we make two approximations, or for approximations and assumptions for expediency in computation. One of them is we prioritize the measurements that we choose to receive at any given time. This is a very large system. We can correspondingly get a much larger set of measurements. But again, that places a lot of stress on the communication channels, which is sending us all of these measurements. So we'll prioritize a much smaller subset of all the possible set of measurements. And then we'll reduce the number of iterations that we let the state estimation run for. And so instead of waiting till convergence for our given criteria, we just specify the number of iterations, and then whatever solution we get, we work with it with the understanding that it is an approximate solution. And so for the scheme that we choose to use, the metric that we choose to use for our prioritization of measurements is the power transfer distribution factor, the PTDFs. And essentially what they are is, they are a measure of how much the real power flow on a line changes when there is an injection at some point in the network followed by a withdrawal of the same amount of power at some other point in the network. And what is interesting to note in that is, so this particular chart here shows it's a bar chart of the PTDFs of all the branches in that WEX system, normalized to percentage values along the horizontal axis, and the number of branches that have a value in that range. And what we notice is that for only a very small number of lines actually have a significant line flow change when there is any sort of injection and withdrawal pair that's occurring in the system. And the vast majority of them have very small values of PTDF. And in fact, note that this is a log scale. If you put it on a linear scale, you can barely even see these. It's so small. And so here's a graphical depiction of the process. One thing I want to point out here is that if we choose, say, a cutoff value of 10%, so the line flow change on a line is 10% for some pair of injections, then I end up only having to look at about 50 lines in the system. And the system has about 5,700 lines. So I have a much smaller set of measurements that I can work with. The problem is that state estimation is an overdetermined problem, or we require it to be an overdetermined problem to have a unique estimate. And so we make do with this idea of pseudo measurements. And essentially, this is a depiction of what we are doing at every time instant that we compute the state estimate. At any given instant in time, when there is some power flow on the DC line, we receive measurements that are prioritized, which are, it's hard to see, but some of these, so this is supposed to signify the set of measurements, and some of these, I'm not sure if you can see, are highlighted in red. Might be hard. Is it actually showing up in the presentation?
You can see it on the monitor.
Okay, well, trust me, there are some that are highlighted in red, which are to signify the prioritized measurements. So we only choose to receive those at any instant. And then we put them through the state estimator, and we get an estimate. And this estimate is then used to compute estimates of the line flows for the other sets of lines that we did not receive measurements from. And so that guarantees that we have more measurements than we need, than the number of states that we're trying to estimate. And so that is then fed into the state estimator with the set of prioritized measurements at the next time instant, and that generates our next estimate, and so on and so forth. And so what happens is here, we have some results on as we change the PTDF threshold, so when I say 5%, I mean only the lines for which the line flow change is 5% or more are being received as prioritized measurements. All the other line flows are just being computed as pseudo measurements and fed into the state estimator. So here are some results on the error in the state estimation compared to the power flow solution as the power on the DC line is changing. And generally we see there's some anomalies here, but generally we see that as the threshold increases, which means we require fewer and fewer lines from which we receive measurements in real time, the error tends to grow. And it kind of makes sense because your state estimator now is receiving two sets of measurements, one of which is at the current time instant, but one of the other set is from a different time instant, and your estimator is trying to reduce the disparity as much as possible between those two disparate sets of measurements. So it's going to try and find an estimate somewhere in between, and so that will introduce some kind of error. And the other one is what happens to the state estimate result as the number of iterations are changed. So here, this is something interesting to note, is that after just a handful of iterations, the error in the state estimation more or less stabilizes to a constant value. Like you can go for more iterations, but it necessarily won't do you much good. And so how does the variation of a combination of the PTDF threshold and the iteration change look like as a whole? It looks somewhat like this, where the axis here is showing as the number of iterations are allowed to increase, and the axis on that side is the PTDF threshold in percentage, essentially telling us how many or how few lines we are receiving measurements from in real time. And generally we see that as the number of iterations increases, the error in the state estimate drops and then more or less becomes constant. Does not vary much as the number of iterations goes up. And on the PTDF threshold, we see there are some jaggedy jumps, but we see generally that as we reduce the number of measurements we receive in real time, the error in our estimate tends to grow. And so if we choose in this instance, so there is a matter of some heuristics involved as to what is the ideal amount of iterations to choose and the number of branches to prioritize measurements from. And it's a heuristic argument, but if you think of the long-term sort of implementation here, if you're interested in mitigating those cybersecurity threats, then you would be interested in identifying some set of critical lines from which you'd like to harden your communication channel to make them more resistant to attack. So if an attacker had some more privileged access in identifying the critical branches in a system, you'd still have some resilience in the system in resisting those cyber attacks. So,
what was the vertical axis there?
The vertical axis is the mean value of the error. So here I'm just looking at the.
Bigger?
It's getting bigger, yeah.
Make sure I understand that. Why is that? Because your threshold is.
So
Was that where you cut off?
So right here, when the threshold going up means that
5% is nothing, right?
Yeah, 5. Well, right.
Those are really big ones over there.
Yeah. So I guess what the threshold is trying to say is that if I choose a 5% threshold, then I look for all measurements from all lines for which PTDF value is 5 or more.
Oh, I see.
So going up along. Sorry. Yes, they are magnitude expressed in. Correct. They are expressed in percentages. But essentially, as this threshold is going up, it's saying that I'm looking at fewer lines.
But why are you saying percentage? Why do you need percentage? The magnitude between -1 and +1, right?
Sure, and it can be expressed as a percentage.
Yeah, but why bring in percentage? I'm asking you, what does that give you?
Well, because you can have you can express a line flow quantity change but I'm interested in which is the line that is most sensitive. So a minus value and a plus value of say 0.5 both indicate that they're equally sensitive.
I just don't understand why you want to go to percentage when just using the value is good enough.
If I divide these out by 100, then yeah, then these would right. So it's just a different way of
doesn't give you any kind of insight.
No, it doesn't. It's just the way we're choosing to express it here. That's true. Yes. So here we have the results of the state estimate in tracking a power order. So here the HVDC line, as in the case study that we talked about, the line can ramp up from 0 to its full capacity, which is 3100 megawatts, in about 20 minutes. And so we are interested in tracking that power order in real time as it happens. And for a maximum iteration limit of 5 and a threshold value for the PTDF of 10%, we see that the state estimate, which is in orange here, compares very favorably with the power flow result. So we're able to track it with pretty good fidelity. And so here I have the performance of this estimator when we simulate a threat. So what we're doing here is we're simulating a threat where the line initially has some power flowing on it. It's about 1,000 megawatt. And then our intended dispatch is another 1,000 megawatts for a final line flow of 2,000 megawatts. But the dispatch on its way to being implemented is corrupted to 2,500, so a final value of 2,500. This is, whoops. What the heck? Kevin, can you just click on that video? Yeah, just click on it. It should start running. So here's a simulation of us tracking the estimate and the expected power profile. And then we see here is where we notice that the estimation that we get from our state estimator is going way past what we expected. So the error in that estimation is starting to shoot up. So what we expect versus what we observe is now starting to deviate. And so there's some indication that the system is not behaving as I would have expected it to behave. And so in that case, the final power order, if it were the corrupted power order, if it were to be executed, it would look somewhat like this. The blue here is the expected injection profile that I hope to see. And then the orange one is what I am actually seeing at the end of that implementation period. So the error between these two can be seen in this. The error profile here is telling me that, yes, there is some noise over here, but I can keep it under a fairly tight tolerance. But if the system goes past and implements something else, then I'm going to see this just start shooting up. And so here's another way of looking at it. And again, what detection strategy we sort of choose to use is, again, somewhat heuristic. But if we define this quantity that we refer to as the SEDR, or the successive error estimate difference rate, essentially the estimate at the current time instant minus the estimate at the previous time instant, and then I keep computing that, what am I going to see? Well, for this sort of ramp, I should expect to see my expectation is to see a pulse like this. So while there is no power injection change, I have 0 value on the pulse. And then as I ramp up, I should have a constant valued pulse. But what I observe, if it starts to deviate from the leading edge more and more in time, so I can observe this computation in time and see if this edge starts to deviate by quite a bit, then there's probably some error or there's some kind of malicious tampering of the signal that I had sent. And so
the hacker, the hacker has to do it a little bit at a time.
exactly, and that's sort of the end conclusion. Essentially, what we are drawing here is that we're using state estimation, being privy to knowledge of the system state or the system information. We're using state estimation as a complementary means for cybersecurity threats. And the idea, I'll reiterate, was inherently that if a specific change was requested in a system and that's being implemented, then my observations of that system should correspond to what I sent within some margin of error. If there is a gross deviation between those two expectations, or the expectation and the observations, then there is some problem. And what we can see is that the approach essentially bounds the extent to within which an attacker could modify a power order and evade detection. So essentially, if they altered it to a value wherein it would be unobservable for our given error thresholds, then we wouldn't be able to distinguish it from just a regular power transmission signal. But it's also unlikely, if we keep those bounds tight, then it's also unlikely that they can do severe harm to the system.
A hacker stole the N from your and.
Can corrupt?
And
Oh, yeah, that's right.
yeah.
That's all. I'll take any questions if you have them.
DOE project, right?
Yes.
Very nice.
So how do you validate this in real world?
So that's somewhat a challenging idea to work with, in that no one would want to willingly subject their system to a threat just to be able to test it. And in fact, some of the assumptions that we've made right now are of systems that have not yet been implemented. So like the power order dispatch signals right now are sent over a telephone link. And then basically a person telling another person to implement something. So it would have to sort of wait until these systems evolve to actually send these dispatch signals over a cyber physical layer to be able to validate them.
So the EMS vendor would have to implement this in the state estimator somehow?
Yes, I think so.
But you have to do this for every line? Or only the ones you care about?
In this context, like if we were to look at sort of the general case, we picked two specific buses in the system, but the set of lines would be still largely similar, even if we were to say look at the general regions. So in that sense, it gives us more generalizability in looking between, okay, this is the major power producing area, this is the major power consuming area.
Same thing with AGC.
Yes.
Because every one of those is an injection.
Right. Yes.
So in principle, you could use the same algorithm to a hacker that gets into the AGC.
Exactly. So like a generation ramp dispatch change or something like that could also be looked at with this idea.
Have you talked to any vendors, EMS vendors about this?
I have not. Well, ABB is corporate on it, right? So
Yeah, okay.
they have tacit first dibs on it.
They might put it in theirs.
Yeah. Cool. Well, thank you for coming.